Hello everyone. Today I'm so happy to be here to give the presentation of our paper. Many thanks to all the contributors of the conference. The title of our paper is SalBiNet360 Saliency Prediction on 360 degrees images with a local and global bifurcated deep network. I'm Chunmei from South China University of Technology. Firstly, I will introduce the background and existing problems of salience prediction on 360-degree images. The 360-degree images play an essential role in VR technology. Unlike the 2D images, 360-degree images allow observers to observe scenes in all directions, so their properties attract more interest to the researchers. Predicting human visual attention on 360-degree images is valuable to content creators and encoding algorithms. It can help the researchers understand the behavior of observers when they wear a VR device. Also, it can be applied in the image compression and image cropping. Although the salience prediction modules on 2D images have been studied in depth, unfortunately, there has been relatively little research on the saliency prediction on 360-degree images. Please look at this figure. A is an equilateral image. B is a corresponding ground truth saliency map of A. C is the saliency map predicted by saliency prediction modules on 2D images. We name C as a global saliency map. We can see the global saliency map roughly predicts the saliency near the encounter region, this area of the image. But for other regions that observers pay less attention to, the predictor can't predict them. So some modules utilize the cubic projection to project 360-degree images onto 6 rectilinear images and predict them separately. E to J are the rectilinear saliency maps. The local saliency map shown in D is reprojected from these rectilinear saliency maps. It can finally predict saliency regions, but some regions not paid attention by humans are incorrectly predicted. For example, here, this area is incorrectly predicted. In order to solve the above existing problems, we propose a new framework based on global and local saliency prediction on 360-degree images, which is named as SalBiNet360. It's a new bifurcated deep network with 2 subnetworks, which predicts global and local saliency respectively. By fusing global and local saliency maps using linear combination, we can generate a final saliency map. In addition, we propose a new multi-scale contextual module in the deep network to extract contextual features in multiple scales of 360-degree images. Also, we adopt a multi-level decoder to reduce the gap between the discriminative features from different layers of network. Finally, extensive experiments on two publicly available datasets illustrate that the proposed SalBiNet360 outperforms the tested state-of-the-art methods. Then, next, I will introduce the details of our proposed approach, including the mechanism and two proposed modules. The framework of the SalBiNet360, illustrated in this figure, contains global and local deep subnetworks. The global subnetwork contains three multi-scale contextual modules and a multi-level decoder to extract multi-scale contextual features of 360-degree images. The local subnetwork contains only one contextual module, same as the one in global subnetwork, and a single decoder with a convolution and upsampling operation, which can be reduced redundancy of local saliency map. The details of contextual module and multiple level decoder will be introduced later. In the global saliency prediction, the whole equitangular image is taken into global subnetwork, and the global saliency map is generated. While in the local saliency prediction, rectilinear images are taken into local subnetwork. After a reprojection method is utilized, a local saliency map is generated. Finally, a fused saliency map is generated by linear combination with the global and local saliency maps. Because we don't have a large dataset on 360-degree images, SalBiNet360 has to be pre-trained by a dataset named Silicon that contains 10,000 2D images for training. After pre-training, two subnetworks are jointly fine-tuned with just the rectilinear images. The loss in global subnetwork is defined as follows, where LBCE here denotes the binary cross entropy loss. And here, L normal is a normalized function for matrix CC and NSS. The L matrix in these two formulas denotes the evaluation matrix for CC and NSS. For local subnetwork, the loss is almost the same as the one in global subnetworks, and the total loss of SalBiNet360 is the sum of global and local loss. In the testing step, when predicting local saliency, firstly, rectilinear images are put into the model, and the rectilinear saliency maps generated in local subnetwork. While predicting global saliency, the whole equitangular images are put into the model, and the model directly generates global saliency maps in global subnetwork. Finally, these two kinds of saliency maps are fused by linear combination. Okay, here we finish introducing the mechanism of SalBiNet360. Then we continue to introduce two important parts in our network. The first one is a multi-scale contextual module. This figure illustrates the architecture of the multi-scale contextual module, which can be effectively extract contextual features from different scale of 360-degree images. Each branch in the module contains 3 by 3 convolutional layers with different dilations. Okay, then we go to the second important part. It's the multi-level decoder. Let's look at the figure 4. It shows the architecture of the multi-level decoder. The multi-level decoder is adopted to reduce the gap between the features obtained by 3 contextual modules. The features are updated in the several layers with these formulas. Here, up is an upsampling operation. Con is a convolutional layer, and concat is a channel concatenation. Finally, I will introduce our extensive experiment about SalBiNet360 to demonstrate its superiority in saliency prediction on 360-degree images. In the contrast experiment of the global, local, and fused saliency, it's obvious that the global saliency regions are roughly concentrated in the encoder part of the images. Please look at here and here. While local saliency prediction can finally predict some saliency objects, but certain objects are incorrectly predicted as high saliency, such as the ladder, here the ladder, and the trees, here the trees. From the table and the images, we can see that the fused saliency maps can predict saliency regions well, both qualitatively and quantitatively. Table 2 shows us the quantitatively results of comparison with different state-of-the-art methods. It's obvious that SalBiNet360 outperforms all the other methods in most cases, especially SalBiNet360 significantly improves the KL values, which demonstrates that SalBiNet360 works better on reducing of loss of information in the saliency density distribution. Then we go to look at some qualitative results. From these images, we can see, compared with the SalBiNet360 here, our model can predict low saliency regions and the regions near the left and the right boundaries of images. Please look at here, the left and the right boundaries of the image and the left and the right boundaries of this image. It can be explained that multi-scale contextual modules can extract contextual features from different scales of images. Because of the time limit, we can't illustrate more details of our experiments. Actually, we have done experiments on the selection of the weights infusing strategy, effectiveness of the multi-scale contextual module, and so on. You can go to our paper for more details. Okay, that's all the content of the paper I want to introduce. Thank you.